So let's do a few problems involving prime and composite numbers and, of course, the basic notion of divisibility. So this is based closely on some book problems. Let's try to find an integer that's divisible by 3 and by 7, but not by 21, or explain why such an integer cannot exist. Okay, so let's see. Let's just try, I'm going to try multiples of 7 and see when they're also divisible by 3. It's a fairly simple brute force strategy. Okay, n equals 7, not divisible by 3. N equals 14, not divisible by 3. Okay, n equals 21, yes, divisible by 3, but no, because we're not supposed to be divisible by 21. Oh, darn it. Okay, but at least it was divisible by 3. Now, not too shocking, because it was, in fact, 7 times 3. Okay, well, let's keep going. N equals 28. No, that's not divisible by 3. Okay, sorry. Okay, n equals 35. Nope, not divisible by 3. Okay, n equals 42. Aha, yes, it's divisible by 3. It's 2 times 3 times 7. But no, because, oh darn it, it's not. It's one of those ones that's divisible by 21. Okay, it seems like, and let's look at this one. This is 7 times 6, or 3 times 2. Okay, but of course that is 7 times 3 times 2, and so it's divisible by 21. It seems like every time we ratchet around and have these multiples of 7 also be divisible by 3, they're also divisible by 21. Okay, so it looks like we would conjecture that this is impossible. Okay, and in fact, we might conjecture that it's a general fact. Maybe when like A divides N and B divides N, we must have the product AB dividing N. That's what we were trying to violate. We're trying to have something where N was divisible by 2 numbers and not divisible by their product, and we seem to not be able to have that happen. Okay. I'm just going to put an here because we haven't done nearly enough work or examples to do this. And this is something where I ask students, and our book asks students to experiment. And if you just do this much experimentation on a problem where it says conjecture, experiment, look at numbers, you're definitely not doing enough work. And we'll see that in the next example. Okay. Notice I'm calling this a conjecture. I'm not calling that a theorem. We have not done enough work here. So let's do another example. And I'm purposely going to note, you know what? There was something pretty special about these two numbers. They're both prime. That's really, really special. And that might have something to do with what we're seeing here. Okay, so let's try the same strategy here. Let's go by multiples of the bigger of the two numbers, just because it's going to be quicker. N equals 15. We want something to, so here's the new problem. We want something that's divisible by 15 and by 10, but not by their product, 150. Or explain why such an integer cannot exist. The big conjecture from the previous problem is maybe it's impossible, but we'll see it's going to be different. Okay, so n equals 15 alone, that's not divisible by 10, doesn't end at 0. Okay, n equals 30 though, right away, oh, yes, and yes, yeah, it really does satisfy both conditions, extra conditions. It's divisible by 15, by construction, it's 15 times 2, and it's divisible by 10, but it's not divisible by their product, 150. Okay, let's see what's different here. This is, we constructed it as 15 times 2, just the second in the sequence of multiples of 15. Okay, well that is, let's go ahead and prime factorize it. That's 2 times 3 times 5. Hey, you know what? That 5 can be used not only to show that it's divisible by 15, but because that's a factor of 10, it can be used to show that it's a factor of 10 as well. And so that 5 gets shared. Because it's a shared factor of 15 and 10, it can be shared in this calculation. And it doesn't have to be, this thing doesn't have to be a multiple of 150. Note that 150, 15 times 10, that is, if you prime factorize it, that's 3 times 5 times 2 times 5. And that's 2 times 3. But then you get the 5 squared, and you know what we discovered is to be divisible by 15 by 10, you don't need 2 5s. You just need to have 1 5 so that you're divisible by 15, and 1 10 so you're divisible by, or 1 5 so you're divisible by 10. You don't need the 2 5s at all. Okay? And so this is just too many 5s. It's not necessary to be divisible by 150. Okay? So what we've shown is that this shows the big conjecture to be false. Okay, and note that, of course, 15 and 10 were not prime. And what seems to be, I'll give a lot away here, it seems to be the crucial thing is that they shared a factor, which of course can't be true if they're both prime numbers, but it's a different thing. Okay, so we're going to be investigating exactly these questions about divisibility, subtle things about divisibility, and they often have to do with primality, but they often have to do with little more subtle interactions between two numbers as well. So this is the kind of experimentation that's great to do. And I wanted to show an example in number 1 of the kind of conjecture you might make. And it's fine to make this kind of conjecture, but just realize that it just might be false, especially if you're only going on one example, and especially if there's anything special about your example. Okay, I'll do another problem in a second video of a bit of a different type where algebra comes in.